It is a pleasure to have Wlodzimierz Bryc presenting the last talk of the day. Wlodzimierz is a professor at University of Cincinnati, now visiting UW as part of his sabbatical, and he's going to be talking about martingales and the rest of the time.
Thank you very much for the invitation, and especially to Chris Burzi for making this visit possible. And it's a real pleasure to be here with beautiful weather and sun, and I didn't expect any of this. So let me point out first the invisible things on those slides. The lower part of the slide is difficult to see, so my talk is based on several works, several papers with Jacek Wesolowski. Some of them are in progress, some of them already appeared, some of them are on archive. And I apologize for the too long title, so let's just not try to read it. So let me begin with a picture that comes to mind of a person who visits a seismic zone and is not used to living in it. So what this is a mathematical mechanical rendering of a simulation of a Markov process. I used 2,000 points for the rendering, and here you see 180 or 200 points or so. So it is clear from those pictures that something is happening around t equal 1, maybe. I don't know whether that's clear or not. And the first part of the talk is to try to convince you that t equal 1 is where things happen. And then the second part of the talk is to somehow try to see how can we see this kind of things if we were not able to, this is a simulation, so I know, of course, when things happen, and, if you were to observe a thing like this, what kind of information could we get from observations, perhaps? So it is fairly obvious when you look at the beginning of the trajectory of this process that the process is actually following straight lines and, a line, and then what do I use there? Maybe I will be old-fashioned and use the mechanical pointer. So the process follows a line, then jumps up on the next line, then follows a line, jumps up, and sort of obvious that that's what it does at the beginning. And it is also obvious what it does at the end. It follows a line, then jumps down, follows a line, jumps down, follows the line, jumps down. This is easy to see on this. This is not so easy to see on this part because this is just 200 points. So, of course, we are missing lots of those jumps. So let's add more lines. This is much less convincing. So this is on authority that these are the right lines. Some of the points are on those lines. Some of the lines go, I think, without any points. Let's add more lines on the right. Let's add a little bit more lines. So I'm trying to say that since I know how the process was simulated, t equal 1 is a special point. That's where the lines change, sort of. So, slightly to be more convincing, here is all 2,000 points, and then fewer lines are missed. But I think some lines, like this line here, seems not to touch anything still. So you cannot really see this kind of picture by looking at by observing a process every millisecond or every. You cannot really see that t is equal 1 is special. So let's try to look at this picture and try to see, can we see things from some simple statistics of the process? Can we see that t equal 1 is special from, say, the mean? Well, of course we cannot. This is a process that has mean 0. How about the covariance? Well, this process, I know I made it up, so I know that it has covariance minimum as t. So again, t equal 1 doesn't show up too much there. Well, there is a situation. There is something that t equal 1 is a little bit special. This process is actually time invertible. That is, xt has the same distribution as t times x1 over t. That's the same scaling as the Wiener process has. The same time inversion thing. So the moments are not helpful. I had a friend in physics that I took to heart his advice when he was studying physics, and he said, you are studying those distributions like normal and whatever. He said, this is stupid, he said. The only thing we can measure in physics is averages. So you should study averages, nothing else. Okay, so let's go to this and say, let's study conditional averages. Let's be, a little bit at least. So this process is a martingale as well. That is, expected value of xt given past sigma field is xs, and it doesn't matter whether t is bigger than 1 or smaller than 1, whether s is bigger than 1, smaller than 1. We cannot see anything out of this either. Well, if you want to study higher conditional moments, for example, conditional variance of this process given the past is a polynomial in xs. If you were to study higher conditional moments of polynomials of xt, they would be polynomials. And in fact, you can produce polynomial martingales for this process. So nothing special here. Well, let's continue the game with conditioning. Let's look at the two-sided filtrations, where we condition with respect to past and future. So we have FST is the sigma field generated by past of the process to the S or future to the T. And let's condition here and see what happens. So if we condition process xt given past and future, then what we get is essentially a linear interpolation between 2 points on the graph, xs and xu. And this is what sometimes people call a hardness condition. And so this process is a hardness. And t equal 1 doesn't show up too much, or not at all here. Well, let's look into the conditional variance, the next thing, sort of next higher moment. One can compute the conditional variance for this process. It comes up as a sort of strange expression. There is this constant that I will be often suppressing in some formulas. And then you have linear function of increments of the process, xu minus xs over u minus s. This other thing looks mysterious, but these are actually increments of the time inverse of the process. You can rewrite this as increments of this process. So it's sort of, time invertibility is hidden here. So we don't see that t equal 1 is anything special. But for people who, there aren't that many, but Jacek Wesolowski, me, and a couple more people, for people who play with conditional moments of processes, we sort of develop these heuristics that if you know the first two conditional moments of the process, including the two-sided conditional moments, then you actually know the process. So somehow all of those things that don't show that t equal 1 is special, somehow t equal 1 should show up in those here on the blackboard. So basically that's what the next part of the talk is trying to say, try to show you how t equal 1 is hidden in those formulas somehow. So what happens is you can sort of decipher that t equal 1 is special if you look into, should I say, bridges of the process, conditionally, condition process on xa and xb, fixed 2 moments of time, and then try to look at conditional moments there. So conditionally on xa and xb, the mean of the process stopped being 0, of course. It's a linear function of t, and alpha and beta are, of course, random, depend on xa and xb. Conditional variance is, so covariance of the process conditional on xa and xb is, well, it's a linear function of s and t, and it disappears at the endpoints.
Did you mean to write x1 there in the second line or x8?
No, I meant to write xa.
Okay,
thank you. And later on, I will mean to write x1, yes. I even didn't notice that, yes. Thank you. So time reversibility, so the first kind of things are lost. So time reversibility is usually lost unless you happen to choose conditioning times and the values correctly. On the other hand, the other part, the two-sided conditionings, those are not sensitive at all to xa and xb because xa and xb are in the sigma field. So the conditional mean is still the linear function of xs and xu. Conditional variance is still the same quadratic polynomial that we had previously. So all of this looks sort of the same. And what I would like to say is that if we convert this situation to standard form, then the two-sided conditional variances of bridges based on xa and x1 on the blue part will be similar to the bridges based on x1, xb, and different than the generic bridges based on xa and xb. I'll be mostly doing x0, x1. x0 is 0, so I don't have to worry about conditioning. And the next thing that I should explain is what do I mean by standard form. So we typically, since the process is a hardness, we sort of developed a terminology calling it a quadratic hardness. If you want, we can call it a quadratic hardness in standard form. If the first two moments are like in the previous slide, that is the mean is 0 and the covariance is like for the Wiener process, and the process is a hardness, so expected value of zt given past and future is a linear function of zs and zu. If it is a linear function of zs, zu, the coefficients you compute from the covariance. One other thing that perhaps I want to mention is that if the process is a hardness and the covariance is as here, then the process is also a martingale. So you can pass with u to infinity and sort of show that the contribution disappears. So the hardness that happens to have the covariances in point 1 is also a martingale and also reverse martingale. So number 2 is the soft assumption, linearity of regression plus you compute the coefficients from the covariance. Number 3, it looks very scary, so let me say that I view it as a soft assumption. That is, the soft assumption says that the variance of zt given past and future is a quadratic function of zs and zu. And one can prove that under some technical assumptions, this quadratic function cannot be arbitrary. It has to be of the form an explicit expression, which I don't want to write, and then it's a quadratic expression in increments of the process, so linear function of zu minus zs over u minus s, quadratic term, the linear coefficient and the quadratic term for the time inverse of the process, and then this cross term, the cross product of the sort of increments of the powers with respect to past and future. So basically,
Get for the winner process.
the right-hand side is the value that you get for the winner process. You get 0, 0, 0, everywhere zeros. The conditional variance is constant. The right-hand side for the Poisson process is you get this coefficient, nothing else. The right-hand side for the process that I showed previously has eta equal 1, theta equal 1, the rest was 0. And you may say, do such processes exist? That's a separate question, yes. So, okay, so basically what happens is if I look at the bridge of the process that I had previously, which was sort of quadratic hardness in standard form, once I change to a bridge, then it loses some of the properties, but things that it loses is the covariance. The covariance is wrong. So the covariance can be easily corrected, and here is an example. How do we correct for the covariance? The simplest example to think of is a Brownian bridge. So a Brownian bridge is a Gaussian process with a covariance that happens to be of the product form, like for all of the bridges of those processes, s times 1 minus t. And other than that, of course, it is a hardness. The conditional expectation of xt given xs xu is a linear function of xs xu. It has to have the right coefficients. I forgot to say that this hardness condition is compatible with more covariances than minimum st. And the conditional variance of xt given past and future is, I wrote xs xu because of Markov property really, is constant, so quadratic. So this is sort of a hardness, except it's not in the quadratic hardness, except not in the standard form because of the covariance being sort of messed up. But then everybody knows how to correct for this messing up, everybody at least who is as old as me and had to study from the 68 edition of Billingsley, the convergence of probability measures. So on page 68 there is an exercise there that says, take a Brownian bridge, do this transformation, and the transformation is not that complicated. It is really a Mobius transformation of time multiplied by the denominator of this Mobius transformation. This is exactly what you need to correct the covariance from this form s times 1 minus t to the covariance being minimum st. Now, of course, this means that you convert the Brownian bridge into a winner process. And you can go backwards and you can say, okay, so now I can compute this in terms of that. In other words, I think I called one of them W. I think Y I call W now. And the Brownian bridge can be written backwards as 1 minus t times the winner process applied to the same type of transformation. So it's a fine function, it's a Mobius transformation multiplied by a linear function of t. So let's look at our process that we were talking about. Let's look at the blue part, and let's look at xt conditional on x0, which is 0, and x1. Well, then this process can be written, transform into the standard form, and if you go backwards, then it can be written as 1 minus t times Poisson process. It's exactly the same transformation that we saw for the Brownian bridge. So it's 1 minus t times n Poisson process at t times 1 minus t. Now the Poisson process, of course, has a parameter lambda. Well, everything should be conditional on x1. So the parameter lambda of this process should be, oh, I forgot to say that this is centered, so that, you take mean 0 first, so you subtract the mean. So NT is a centered Poisson process with parameter lambda, but lambda now is a random variable. Lambda depends on x1. Well, not in a very complicated way. Lambda happens to be 1 plus x1. And furthermore, we actually know what's the distribution of lambda. It happens to be exponential. And then if you look at the black part of the trajectory, what happens if if you look at xt being bigger than 1, conditional on x1, x infinity is 0, really. We should look at this way. Then xt for t bigger than 1, conditional on x1, is another Poisson process. This transformation here is really just the time inverse of that transformation. So it's t times x1 over t applied to that thing. And instead of the Poisson process that we had previously, we have an independent Poisson process. So n tilde is an independent Poisson process, but with the same parameter lambda, with the same capital lambda. So the capital lambda is shared between the two processes. So what this really shows you is that I can take two Poisson processes with random parameter lambda, and if I choose the distribution, this was the title of the talk, putting together pairs of Poisson processes into a martingale. So what I did here is I sort of showed how one can put, well, not convincingly, but how one can put two Poisson processes with the same random parameter capital lambda, which happens to be exponential or exponential minus, exponential. And I can put together into a quadratic harness and also into a martingale. So the question of putting Levy processes into martingales by this kind of fashion is, of course, something that I'm not even trying to answer. The question of putting together Levy processes into a quadratic harness is slightly easier to answer because there are very few quadratic harnesses among Levy processes. Well, okay, so let's look back into the sort of a question slightly, in more generality. So suppose that we have a quadratic harness ZT, which has covariance minimum ST, mean 0, it has a harness condition, and also has this quadratic variance with all of those 1, 2, 3, 4, 5 parameters floating there. And what we want to ask is, when else this situation happens that we saw previously? That is, when is it that we can find a capital T moment of time t, such that the left-hand side of the process, this blue bridge, for t is smaller than capital T conditioned on the value of zt, in the standard form becomes a simple enough quadratic harness. What do I mean by simple enough quadratic harness? Well, it has some parameter theta, some parameter tau, and the increments of the process. If y was supposed to be a Levy process, then conditional variance of yt given fsu would have to be a function of increments of the process. It would have to be perhaps not a quadratic function, but for quadratic harnesses it must be a quadratic function. I also left rho there because we actually can allow this cross term as well, and the theorem still is the same. So then essentially there are only three situations that this happens. One situation is sort of boring. So all the parameters here are 0. Well, if all the parameters here are 0, zt is actually a winner process. One can show that. And then, of course, you can choose any capital T and all of this happens, but that's a boring case. The other possibility is that the upper part is there, but the lower part isn't. So there is no quadratic terms. And I think we assume that eta times theta is positive. In my example, eta and theta were 1. Well, then this is the example that we saw. This is the pair of Poisson processes that one can glue up, so that, I'm not saying that's obvious at this point, but the next slide will make it more obvious. What one can do is one can compute, if you know what are the parameters of the original process, you can actually say what are the parameters of this bridge. That is, you can say that the conditional bridge in the standard form, this is complicated in a sense of it is an ugly computation, so it is good to have good notation, but one can compute those numbers in terms of the original numbers and in terms of the conditional variable zt. And therefore we can sort of read out what is the process. So the process here would be actually corresponding to this case that we were doing in our example. And the third possibility is that you have all the parameters really there, eta, theta, sigma, tau, and rho, but they are not arbitrary. Rho is actually at the upper range of its availability, that is, it's 2 times square root of sigma tau, and eta and theta are also somehow tied by an equation with sigma and tau. And then the moment of time that we are interested in is square root of tau over sigma, and then the process itself, we can recognize what it is, which is the next slide. So the next slide is the theorem of Wesolowski that says, what do we expect from the process? In each case, there is only that many parameters. The third one that I allowed for the process turns out to always come up as 0. And that's why I sort of could allow it, because it doesn't matter. So this is the slide that is supposed to be answering what kind of processes can you get as bridges of quadratic harnesses, if there is this special moment of time, capital T. So the only ones that you can get is the ones that have theta and tau there, and then we can actually show that such a process has all moments, and we can show that it has martingale orthogonal polynomials, and we can identify the actual process, that has to be a Markov process, which we know. So one of them is possibilities is that Y is the winner process. If we happen to have no tau but linear term, then Y has to be a Poisson process. If we happen to have full quadratic form, then everything depends on whether this is the positive definite form or sort of negative definite form. So if theta squared is bigger than 4 tau, then this is a negative binomial process. Well, I say type because what I mean is affine transformation. That is, I'm requesting Y to have mean 0 and covariance minimum as t. So you have to multiply Poisson, you have to subtract the mean of the Poisson process, you have to scale it by something related to lambda to get there. And then if this happens to be a complete square, I thought, but maybe this is not a complete square, but theta squared equals 4 tau is when yt is a gamma type process, so you have a gamma process. And the third possibility is, unfortunately, lesser known process called hyperbolic secant process. So basically what I'm trying to say with this slide is that if you are interested in putting together pair of processes like I did with the Poisson process with this one example, then the only options for such processes are really, the only interesting options are Poisson process, negative binomial process, gamma process, or hyperbolic secant process. These are the only processes that are worth trying to randomize parameters in them and trying to put them together into a quadratic harness. So, well, I mean, one would like to put a quadratic harness, but the trouble is that, so we sort of know the distribution of the bridge, and we sort of know the distribution of the right-hand side bridge. What we are missing is the distribution of Z1. I mean, I said Z1 happens to be 1 plus Z1 happens to be exponential in my particular construction. And somewhat simpler version of the question is to say, let's be not too ambitious. Let's not try to put things into a quadratic harness. Let's just try to put everything into a martingale. So a pair of two independent Poisson processes with parameter capital lambda, if capital lambda has exponential distribution, then we can actually put them together into a martingale. Are there any other capital distributions that we could use? Or we can take a pair of negative binomial processes. These are Levy processes, so I'm just writing the distribution of yt, which is this ugly expression, and there is a parameter pi which is random, and can we find a pi that this will make a martingale? Well, quadratic harness perhaps, but at least a martingale. For the gamma process, the natural randomization to do is actually, the gamma has two parameters, and the scale parameter is what you want to randomize. So you can just as well say we take two independent gamma processes with x1 being exponentially distributed. And we ask, can we make a martingale out of those by changing time correctly and by choosing the distribution of multiplier W correctly? And then hyperbolic secant process. Luckily, the slide is hidden so that most people cannot see it, and that's good for you because, because the density is ugly and has gamma function in it, has e to the alpha x in it, and has parameter alpha, which is in the interval minus pi pi. That's the parameter we actually want to randomize. Well, so you sort of saw the answer for the Poisson process at least a little bit. So let me try to say first sort of, so there's this, we have this 5 or so theorems that are all identical. And one of them says, suppose that the process is conditionally negative binomial. And then suppose it is conditionally hyperbolic secant. Suppose that this, suppose that that. So suppose that we have a yt for now, one of those processes, the yt and yt tilde later, happens to be conditionally negative binomial process. Well, the first thing that sort of surprised us is that no matter what the pi is, the process is actually Markov. I mean, maybe for the audience here that's obvious, but for me, for us, it was a surprise. Then this process is a Markov. Then if we assume that this pi has enough moments, so 1 over pi is square integrable, then we can sort of make out, this is one of those transformations that we were talking about. So in other words, I can transform the process y into a new process zt by this affine function, Mobius transformation, not that complicated, not that different from those things that we saw previously, times 1 minus t and subtract the mean. And that will make it into a quadratic harness for all the t's that are available here, so all the t's in the interval 0, 1. And you can compute the parameters which you don't care. And the value of C also depends on the moments, variance and mean of the randomization thing. So basically what this says is that every random variable pi will work to produce a harness. Will that make us a martingale? Well, I said previously that harnesses are, without even quadratic harnesses, just harnesses are martingales. Harnesses on 0 infinity are martingales because you can pass with u with the right-hand side conditioning to infinity. Harnesses on 0, 1 don't have to be martingales. So this is actually typically, I mean, this yt over zt over t or something like this is a reverse martingale. But it is very rarely a martingale. So here is a theorem that says when is that a martingale, the thing that we constructed that I described a moment ago. So suppose I take this random variable pi such that it has the first moments, and suppose that y is this pi conditionally negative binomial process, and that zt is given by this kind of transformation, except I am not even assuming the second moment of pi, so I'm saying there are some coefficients that make this a martingale. So I say, suppose that zt of this form is a martingale. Well, this is equivalent to pi having a very explicit density. This is equivalent to pi having a beta density, essentially p to some power times 1 minus p to some power times the normalization, where a and b depend on what you used in the normalization, and this works out backwards correctly so that then this random variable has the variance, and then all of those things match together. So I don't know how known is this theorem. So originally we proved this for all 5 processes, and we were fairly happy because every time we proved this, we sort of had a proof. They were similar, but they were not exactly the same. And then eventually we ended up thinking, well, wait a minute, we have a new property of a Poisson process because we have a similar thing about the Poisson process as well. And then we thought, is it realistic to expect to have a new theorem about the Poisson process? So then we should have used Bing, but we used Google. And we found a paper of Nekrutkin from 2007 that was essentially saying martingale property of randomized Poisson or something like this. Or maybe it was saying Polya processes as randomized, but there was definitely this was exactly this kind of result except for Poisson process. But then once we found this, we sort of said, well, why don't we search more? So once we searched more, we found a paper of Diaconis and Ylvisaker on conjugate priors for exponential families. We wouldn't ever look into that paper without Google search, because this looks like complete statistics and appeared in Statistics Journal, and it's fairly old too, which has exactly the mathematics that leads to this. I mean, it has more general mathematics because it's all conjugate priors for all exponential families, but surely it implies this result. It doesn't actually imply Poisson case for some technical reasons about the support. So for Poisson case, one has to go back to a paper of Johnson from 1957, which does the same thing, but only for Poisson case. So once we know this, what we do next is we say, well, I'm still continuing this example of negative binomial process, just not to repeat the Poisson every time. So suppose now that I take y and y, I should have used tilde like previously, but I forgot, to be pi conditionally independent negative binomial processes, and let's assume that pi has mean and the variance. And then we define this process, that's the previous definition of the process that I used for Martingale. This is time inverse of this process with y prime. And this is what I need to do in order to assign the value for t equal 1. So this is 1 over pi standardized. This is 1 over pi minus its mean over the variance. I'm supposed to have covariance of zt the variance of zt is supposed to be t. Then by construction, this process is time invertible because I use the same formulas, the time inverses of the formulas here and there. So actually this is time invertible process. And then I can sort of prove a great theorem that says, well, the following conditions are equivalent. Zt is a quadratic harness on 0 infinity. That's what I want to get, really. Well, if it is a quadratic harness, part of the definition, it is a harness. So, okay, 1 implies 2, QED. Well, if it is a harness, then it's a limit only to take. Harness with minimum ST covariance implies a martingale, so QED. And the last fact that I showed you, Diaconis Ylvisaker, if Zt is a martingale, then on all t on 0 infinity, I should have said, then it is a martingale on 0, 1. If it is a martingale on 0, 1, then the previous theorem says that pi has this very specific beta distribution. And the only thing that remains to be proven is that 4 implies 1, which amazingly works on exactly the same identities that you get from 3 to 4. So it's sort of... So the same kind of results hold for pairs of Poisson negative binomial gamma hyperbolic secant processes. We actually worked them out. The first couple of them we worked out as exercises because we knew the answer from a paper that we wrote in 2006. So the Martingale condition on 0, 1 determines the law of randomization. And then the correct law allows us to continue the process to t larger or equal than 1. And then the correct law gives us actually a quadratic harness. So this happens for Poisson, negative binomial, gamma, and hyperbolic secant processes. And all of the laws of randomizations with a small disclaimer about the Poisson can be deduced from Diaconis Ylvisaker paper. So we don't really have to work as hard as we did. And in particular, a pair of lambda, so this is sort of a summary of those results saying when can you actually glue together into a martingale, also into a quadratic harness, a pair of conditionally independent Poisson processes. Well, if and only if the randomization has gamma density, which is written here. And we knew this answer, as I say, from the paper that we wrote a long time ago. This is not that difficult to guess that gamma density goes well with Poisson. You can sort of do various formulas. A pair of pi conditionally independent negative binomial processes makes a martingale on 0 infinity, or a quadratic harness if and only if pi has this beta density. This perhaps I wouldn't be able to guess, but Jacek Wesolowski was able to guess, and we sort of based on various analogies between those two formulas. And this kind of theorem that you get a quadratic harness with this density is actually a master thesis student wrote up, the complete proof, unfortunately available only to people who read Polish, because it's in Polish. So this is sort of student type assignment. Then a pair of gamma processes with multiplied by random variable makes a martingale on 0 infinity if and only if W has 1 over W has a gamma density, or W has this density, which is the density of 1 over the gamma. And this result is also easy because you can get gamma process as a limit of negative binomial processes, and you can read out the answer. You can read out what randomization you can need to do. So we did those 3 cases solely to learn how to recover from martingale condition the density so that we would know when we knew the answers, solely because we had no idea what to do with hyperbolic secant process. So here is the answer for hyperbolic secant process. Well, the hyperbolic secant process has this parameter alpha, which is between minus pi and pi, and this is a martingale. The pair of 2 conditional independent hyperbolic secant processes are a martingale and also a quadratic harness, if and only if the density of the randomization is given by, I don't know how to describe this. I think we even don't know the normalization constant. I think we didn't compute that. So this law defines Z1. This law defines the law of Z1 for the decomposition of a quadratic harness into the Levy bridges that I was talking about in the previous theorem. So I have 2 minutes for conclusions. So one thing that I want to say is that after going through all of those exercises, I would be able to recognize the existence of this special time capital T if you give me a process that has 2-sided regressions that are linear and conditional second moments, and the product covariance of this form. If you would give me all the parameters, then I would be able to tell you whether there exists a capital T like this or not, essentially by computing various algebraic things about the parameters. And then if this will happen to be the case, then I would be able to tell you whether that's a pair of Poisson, negative binomial, gamma, or hyperbolic secant processes. So the example that I was showing in simulations was the Poisson process. The Poisson and negative binomial process, if you really were able to observe trajectories, you see that they follow lines and go up, and then the time reversal of the process, so it goes, follows the lines, goes down. The other 2, gamma and hyperbolic secant, this, even if you saw all the trajectories, I think you wouldn't be able to read that there is anything special about t equal 1. I don't know how. There is infinite number of jumps before t equal 1 and infinite number of jumps after 1. In all of the cases. And I guess I squeezed the talk into 40 minutes, so here are the 2 authors, and here is the person that was hiding on the lower part of the slide.
Okay, so I just want to make sure that I really understand the philosophy of this project, because it seems to me that, the first question is, why would you want to construct a process from 2 processes? If you
Well, I mean...
Okay, so I'm trying to guess, because there was this joke about the earthquake or something, so basically, are you saying that this is supposed to be a model for some phenomena where there's a distinguished time?
I would like it to be, but of course not for earthquakes, because they are spatial and so on, and there is this, I forgot, something law, which the something law fits those processes, but everybody uses modified something law, where you put a power law instead of a 1 over t type things. So the intensity of jumps for this process on the interval 0 to this capital T is of the form 1 over t. So I don't know, does that make it a good model for earthquakes? Probably not, because they are spatial as well. So I would like it to be models for something, but our original motivation was that you can write down this quadratic harness formula and you say, let's consider a process with the following conditional moments. Do those processes exist? So we were largely in the business of saying, can we construct a Markov process that would be a quadratic harness with the following parameters? It's part of that sort of bigger strategy of finding processes, enough examples of processes.
Okay, so let me follow up with a much simpler question. And you might have already answered me. Harnesses appeared in a recent paper of mine, and with Shumik Pal, and we just said in that paper that there are some simple examples, Levy processes, and there are bridges. So is there some kind of theory or characterization of all harnesses or interesting harnesses?
Harnesses, there's, I think, too many of them. Harnesses that have also second-order moments, that excludes, for example, lots of Levy processes. There's only 5 of them. So there is better hope for that. And for this, there is almost a theorem, meaning modulo technical assumptions, they all have orthogonal martingale polynomials that are Askew-Wilson polynomials, except those. Those are actually outside of those Askew-Wilson polynomial scheme. And they are not limits of those either. So in a sense, this is, we are playing a game of, here is the set of parameters that you can put in this quadratic form. We know what happens here, we know what happens there. Well, here is the boundary that we don't know what happens. That's the boundary. And there are still unknown regions that we don't know what happens in some regions between this boundary and the other boundary which you get from Askew-Wilson polynomials.
More questions? Let's thank the speaker.